All right, anybody have any questions? Yes.
Number 10 on internal loads and beams.
Mm-hmm.
You had us get the what did you get us to do? You had us get the max shear stress for points on the left half of the beam.
Mm-hmm.
You had us do everything for the right. So when we have max shear, we've got it at the. You had us get the stress tensor for the top of the beam and the bottom of the beam.
Is this for stresses in beams?
No, sir. It's
Oh, that was the problem that was sort of in the wrong spot. Okay.
So we're trying to find what? The maximum?
max shear stress for points on the left half. And we calculated it because we had to do we got a stress tensor for the top of the beam and then a stress tensor for the bottom of the beam. Do we get the greatest magnitude is going to be the greatest, that's the greatest principal force that we use to.
Yeah, that's a good question.
That's what it looks like you did in the solutions.
Yeah.
Or do the bending moments cancel each other so you just go off with the tension?
No. Okay, so let's, can I see that problem?
Yes, sir.
Yeah, finding the max of any kind of stress is a pain in the butt.
So that's the one where so this is number 9.
Number 10.
Oh, number 10. Okay, so first we have to calculate those internal loads. And those internal loads, okay, so let's take a cut on the left half. So you have the horizontal force like this. Let me draw this problem. The problem looks like this. You have a cantilever on the right, a beam that's actually straight, 500 newtons like that, a couple of 600 newton meters like that, and then a horizontal force at the midpoint like that. And it asks for a bunch of stuff about the stress on the left half. So if we make a cut on the left half, those are the external loads. And then the internal loads look like this. There's no torsion in this problem, so I'll just leave it out. So Newton's second law says 500 0 plus T negative V is equal to 0. So T is equal to negative 500. V is equal to 0. That's going to make this problem a lot easier, the fact that the shear force is 0 on the left half. And then the rotational equation, we have positive 600 plus m minus Vx is equal to 0. So m is equal to negative 600. So none of these vary with x. These are constant anywhere on the left side. So now we can just think about up and down on the cross section because we don't have to worry about what happens as x changes. So we know that the total stress tensor is equal to the stress tensor due to tension plus the stress tensor due to the bending moment plus the stress tensor due to the shear force, plus the stress tensor due to the torsion. This is 0. There's no shear force, so that's 0. So we only have to worry about these two. And so all the stress is going to be in the x, the XX element. That's the only non-zero element for the stress that we're going to have. So the maximum shear is going to be wherever we have the biggest absolute value of XX, because then if you think of the formula for the max shear stress, you just take the maximum normal stress minus the minimum, the maximum principal stress minus the minimum divided by 2. So if you get a bigger maximum or a smaller minimum, you get a bigger shear stress. But you do have to worry about the interaction between the tension and the stress due to the tension and the stress due to the bending moment. So let's first think about the tension. T is equal to negative 500, so sigma xx is equal to negative 500 divided by, the height is 0.1, the width is 0.02, so divided by an area of 0.002. So I believe that's 2.5, negative 2.5 times 10 to the 5.
Yeah.
And then the bending moment. Okay, so we have a stress due to tension that's equal to negative 2.5 times 10 to the 5, 0, 0, 0, 0, 0. And here we're going to have an XX stress that's equal to negative my over I. So let's put aside what I is for a minute. The bending moment was negative. So this is negative of negative 600 times y over I, or positive 600 y over I. The biggest XX normal stress we can have is when this is negative, as negative as possible, because then you have the effect of it adding with the negative stress due to tension. You follow what I mean? If we have a positive value of the XX stress due to bending, then it negates some of this negative stress we have here, and you're going to end up with a smaller total absolute value of the normal stress, and then you're going to have a smaller maximum shear stress. The max total EXX is when y is a minimum, because that's what makes this value negative. And the lowest it can be is 0.05. So y equals negative 0.05. And then you have sigma xx is equal to that should just be equal to 30. Negative 30 over I. Whatever I is, you can get a number for that. And so the stress tensor is equal to negative 30 over I. Then add these two to get the total stress tensor, and then use the formula for max shear stress to get the maximum shear stress.
Right. that was my question though, was, you know, the greatest magnitude when everything's added together
Mm-hmm.
to get the
Yeah, so
shear.
in this case, it's a lot more complicated if you also have a shear force, because then you have to deal with shear stresses that are all, you know, but in this case, what we have is we have a stress tensor that's already a principal stress tensor, and then you know that your sigma, your tau max is just equal to sigma max minus sigma min. Those are the principal stresses divided by 2. Any other homework questions?
Thank you, sir. Yep.
Okay, so the last thing we have to do to come up with stress tensors for points and beams is to talk about torsion. And the effect that you get is like this. If you have an object, I'll draw it with a round cross-section, but this is true in general. And you put a torque on it like this, and the equal and opposite torque on this side. What you're doing is rotating this end this way, and this end this way. And so if you start with an element like this, after the deformation, after you apply this torque, this is exaggerated, but you get an element that now looks like this. Okay, that's the change in shape of that square that comes from this torque. And because of the way that square deforms, it makes sense that this corresponds to a shear stress this way and this way. And then for it to be in equilibrium, you also have to have one like that and like that. So this picture illustrates the relationship between an external torque and shear stress. Okay, so what type of shear stress is that? Well, that depends on where on the surface this is. If we imagine that we're on the, okay, so if our coordinate system is like this, you know, so like we're to the side of the beam, so there's the z-axis, this is the x-axis, this is the y-axis, then that stress is on the x face of this stress element in the negative y direction. So you get, so this torque corresponds to a negative xy shear stress. Okay, can you visualize that? Think about that for a second. So think about this as this is a stress element. I usually draw it tilted the other way, but so if this is your stress element, you have that, and that. And this over here this obscured face over here is the X face. Okay, so this stress due to torque is an XY stress, right? Well, actually, this is one that changes depending on where on the surface you are, because now imagine that that you're looking at the beam from above. So now your coordinate system, you have the y-axis pointing towards you, the x-axis this way, and the z-axis this way. And your stress element is like this. The directions are still the same, they just correspond to different axis directions. So now, okay, so in the first example, this was a negative XY stress. So what is it here? Well, this is the positive X face again. But now that stress is acting in the positive Z direction. So that's a positive XZ stress. Now imagine that you're looking at this beam from the so like you're looking this is getting too complicated. So don't imagine this. But the take-home message is this. What type of shear stress you get from torsion depends on where you are on the beam, on the where you are on the cross section of the beam. And that's a new thing. We haven't seen that with any of these internal loads yet. Okay, so that's going to be an issue that we're going to have to deal with if we're looking. Okay, so if this is the beam and this is the coordinate system, the x-axis out towards us, the y-axis up, the z-axis to the left, a point over here, torsion causes an XY shear stress. A point here torsion causes an XZ shear stress. We've been getting sort of, with each internal load that we've done, we've been getting more restrictive about what kind of cross-sections are allowable. With torsion, we only have two types of problems that we can do, two types of cross-sections. So we'll do stress for torsion with two cross-section types. The first one is circular, and that can be solid or hollow. And the second one is thin-walled, closed cross-sections. Thin-walled tubes. And these have to be closed shapes, so I'll show you what that means. So we can do stresses in a cross-section like this. Or like this, and the thicknesses don't have to be the same. You could have it thin on top, fat on the sides, in between on the bottom. Those are both okay. But we can't do this or this. These are called open cross sections. Okay, so it has to be, the cross-sectional shape has to enclose some area. We need one mathematical preliminary before we can do these calculations. And that's called the polar moment of inertia. And it has this integral definition. I sub p, that's the polar moment of inertia, is equal to the integral over the cross-section of rho squared dA where rho is the distance from the cross-section centroid to your infinitesimal area dA. You can calculate this for any shape. You know, that mathematical definition, there's no restrictions on that, but we can only calculate stresses for a limited number of cross-sections. We're only going to use this for circular shapes. When we do thin-walled shapes that aren't circular, we're not going to use this polar moment of inertia. We're going to use a different approach to calculating the stress. So we'll only use this for circular cross-sections. Bless you. So I'm going to go through the calculation from this definition for the circular cross-section. Okay, so let's say we have a hollow circle. I'll call this capital R inner and this capital R outer. And we'll define our infinitesimal area dA like this. So it's going to be a thin circular strip where everything on that strip is the same distance from the centroid. And so this distance is what we'll call rho. And the thickness of this strip we'll call d rho. Then what's the area of this strip? How would you figure that out? This trick comes up in so many of these integral uses of the integral definition. You should get used to this way of thinking about it. So dA for this strip, think about cutting it at some point and then taking it and stretching it out into a long, skinny rectangle. Then the area is just going to be the thickness, using the area for a rectangle, the thickness times the circumference. So dA is equal to 2 pi rho d rho. And then the polar moment of inertia is the integral of rho squared times 2 pi rho d rho for all rho values between R inner and R outer. And so you get, we'll pull the 2 pi out. Now we have the integral from R inner to R outer of rho to the third d rho. That's equal to 2 pi times rho to the fourth over 4, evaluated from R inner to R outer. And so you get pi over 2 times R outer to the fourth minus R inner to the fourth. If it's not hollow, if it's solid, then R inner is 0, and that term just goes away, and you're left with, so for solid, you get that the polar moment of inertia is just pi over 2 times R to the fourth. Okay, so given this definition, for a circular cross-section, the shear stress is equal to negative that should be T, so negative torque times rho divided by I sub P. And that rho is the distance from the centroid to the cross section to the desired point. And the way we're going to figure out which elements of the stress tensor this is we're always going to do it with, so we'll always do this calculation in a temporary coordinate system, a temporary capital X, Y, Z coordinate system. With the origin at the centroid and the capital X axis, no, not capital X, capital Z axis. The capital Z axis pointing toward the desired point. Then we'll just use rotation matrices to re-express it in the coordinate system we want. So then we'll use the Q matrix to express it in the correct coordinate system. Okay, so in this formula then, go up here to the shear stress, and that is going to be the capital X, capital Y shear stress. That's not saying that it's going to be the XY shear stress in our permanent coordinate system, but this is what it's going to be before we do the coordinate system rotation.
Can you draw the coordinate system on this example again?
Yeah, so let's, okay, so for example, if this is the cross section, and this is the true coordinate system. So the x-axis is towards us, the z-axis is that way, and the y-axis is up. And say that we want to calculate the stress at this point. Then we're going to use that formula in a temporary coordinate system with the capital Z-axis that way, the x-axis, the capital X-axis is still the same, and the y-axis then has to be like this, the capital Y-axis. And then once we get the stress tensor, we'll use a rotation matrix to go from this coordinate system to this coordinate system. So we'll do this with a Q matrix. Any questions about that yet? All right, let me do an example. So let's say we have this cantilever beam with a torque of 40,000 Newton meters pointing to the right. Our coordinate system is like this. The x-axis along the beam, the y-axis up, the z-axis towards us. A cross-section has the y-axis up, the z-axis that way. So this is what the cross-section would look like if we're looking into that 40,000 Newton meter torque. Okay, we're like on the right side of this looking down the axis. And let's say we want to calculate, well, let's calculate a couple of these. Let's calculate the stress here, here, and then let's do it here, where this angle is 45 degrees. The radius of this, I need to give the radius. Let's say it's 5 centimeters. So what are the stress tensors at A, B, and C? Well, first we have to calculate the internal torque. It's constant along this whole thing. Rotational equation along the x-axis looks like this. We have the beam. We have the 40,000 Newton meter torque here. And we have the reaction torque, I'll call it TR here. So fancy TR plus 40,000 is equal to 0. So TR is equal to negative 40,000. And now we'll do a cut. And you can probably see this coming, but this is the way you calculate it carefully anyways. So we have 40,000 Newton meters going this way. We have an internal torque, fancy T, going this way. Rotational Newton's second law about the x-axis says negative 40,000 plus fancy T is equal to 0. So T is equal to 40,000. Okay, so that's the internal torque. And probably a lot of you could have just eyeballed that from the start, but that's what it is. So now for part A, for the point A, we know that the capital X, capital Y shear stress is equal to negative T times rho over I sub P. We need to calculate that I sub P. So I sub P is equal to pi over 2 times the radius to the fourth and you get a value of 9.82 times 10 to the minus 6 meters to the fourth. And if we're looking at the point A, what's the rho vector? Rho is the distance from the centroid to the point that we care about. .05, yep, because we're on the, so anytime you're on the surface, rho is just equal to the radius of the shape. So tau, capital X, capital Y, is equal to negative 40,000 times rho, 0.05, divided by 9.82 times 10 to the minus 6, and you get a value of negative 2.04 times 10 to the 8th pascals. And now how does the, so let me draw that cross section. Our capital coordinate system had a z-axis pointing towards the chosen object. So here was our capital z-axis. Here's our capital y-axis. How does that compare with our real coordinate system? It's the same in this case. So this tau xy is equal to tau lowercase xy. So the stress tensor at A is just equal to 0, negative 2.04 times 10 to the 8th, 0, negative 2.04 times 10 to the 8th, zeros everywhere else. So now let's do the point B. Anyone have any questions about that? Am I going too fast?
Very fast.
Okay. But not too fast.
Not too fast.
Perfect high speed. Yeah. Okay. Sorry about that. I'm going to slow down now.
Why is the XY face again?
Why is this in the XY position?
Yes, sir.
Okay, because if we are, it has to do with this picture. I'm going to draw it this way. And imagine, so this is, I'll do it in red. So this is our capital Y. This is our capital Z. And this is our capital X. Okay?
Yep.
And an element that originally looks like this, if you torque this shape like this and like this, what you're doing is twisting this side that way, this side that way. And so this element deforms like that. And the only way you can produce that is with a shear stress down that way and up this way. And that is on the capital X face in the negative Y direction. Okay, so now let's do B. So we know that tau capital X capital Y is equal to negative torque times rho divided by I sub p. We already calculated I sub p. That's a property of the shape, so that's not going to change based on what point you look at. Our point B is on the surface, so rho is still going to be 0.05. And so this is equal to negative 40,000 times 0.05 divided by 9.82 times 10 to the minus 6. You get the same value you did before, negative 2.04 times 10 to the 8th.
Is that supposed to be for XZ, or is it still XY?
It's still xy in the capital coordinate system, because we're looking at this point B. In our capital coordinate system, we just always aim the z-axis at the point that we want. So now we have a new capital coordinate system. But then we're going to have to use a rotation to re-express it in our real coordinate system that has the lowercase z-axis that way and the lowercase y-axis that way. Okay, so our, I'll call it sigma capital X, capital Y, capital Z is equal to 0, negative 2.04 times 10 to the 8th, 0, negative 2.04 times 10 to the 8th, and zeros. And now we have to think about what rotation matrix we need to go from here to the red to the green. So we have the y-axis, the z-axis. We're trying to go to this coordinate system. So what's the rotation we need? It's going to be about the x-axis.
90 degrees above. Negative 90.
Positive 90 degrees about the x-axis. So plus 90 about x. So the Q matrix is 1, 0, 0. 0 is down the first column. And then you have cosine of 90 is 0. Sine of 90 is 1. Negative sine of 90 is 1. Cosine of 90 is 0. And so the final stress tensor, the correct stress tensor, is this Q times the stress tensor in the capital coordinate system, which was 0, negative 2.04 times 10 to the 8th, 0, negative 2.04 times 10 to the 8th, zeros. And then Q transpose. So 1, 0, 0, 0, 0, negative 1, 0, 1, 0. And if you punch that in, you get, well, I described what was going to happen earlier. If you're looking at a point on the top of a circular cross-section, you're going to have non-zero shear stresses in the XZ elements. And so this gives you 0, 0, positive 2.04 times 10 to the 8, 0, 0, 0, 2.04 times 10 to the 8, 0, 0. Any questions about that? Okay, well, let's take a break, and we'll come back, and I'll do the last one. There's two different things in this one, the last one. Rho is not equal to the radius. That's not too hard to wrap your head around. And then the rotation matrix isn't going to be like a 90-degree thing. So we're going to have multiple shear stress elements instead of just a single shear stress element. Okay, so let's start again at 9 after. Who am I kidding? Am I really going to start at 9 after?
Christ, 8 after.
Maybe. Maybe today's the day I make up for all the other days. Okay, so we're on the last part of this example problem. We're dealing with this beam. And now we're trying to figure out the stress in the green coordinate system at that point C. That's supposed to be at the midpoint between the centroid and the outer surface. Okay, so here's the cross section. This is the point we care about. So the capital Z axis goes from the centroid toward the point we care about. The y-axis is like that. The capital X, capital Y shear stress is negative T, fancy T, times rho divided by the polar moment of inertia. So that's negative 40,000 times, this time rho is half of the radius, so 0.025, divided by the polar moment of inertia, 9.82 times 10 to the minus 6. And you get half what we got before. So that's negative 1.02 times 10 to the 8th. And now we have to think about what rotation matrix we need to go from here to here. So what do we have to do? You could always go two directions. Yeah, positive, so 45 would get the y-axis pointing to the right, and then another 90 gets the y-axis pointing up. So theta is equal to positive 135, and this is always going to be about the x-axis. So the Q matrix is 1, 0, 0, 0, 0 down the column, and then negative 0.7071, positive 0.7071, negative 0.7071, negative 0.7071. I didn't write the stress tensor, but from this value, we know that the capital X, Y, Z stress tensor is 0, negative 1.02 times 10 to the 8th, 0, negative 1.02 times 10 to the 8th, zeros, so the stress tensor in the green coordinate system, the one that we want, is equal to Q times the capital stress tensor times Q transpose. Could someone multiply that for me? I don't have that here. Okay. Okay. Okay, so yeah, no, 7.E7, 7.2E7, and then zeros. Okay, come on, that's cool. It is. And so then this was a problem where the only internal load was torsion. But if you had a beam that the point you're looking at had tension and bending moment and torsion and shear force, you just calculate these stress tensors and then add them all up in the end, and it gives you the total stress tensor. Yeah, so superposition is what lets you add them all together, yeah. Any questions about that?
You have to do the rotation matrix for each one of those, right?
You don't have to do the rotation matrix for any of them except the torsion. That's the only one that we have to do this with. And the reason we have to do that with this is because where you are on the cross-section affects what elements of shear stress you have with the torque, and it doesn't with the other ones. Okay, so that's how to calculate the stress due to torsion for a circular cross-section. We can also do it for thin-walled tubes. And the rule of thumb that I saw in some textbook once. So how thin is thin enough to use this formula? Think of the wall thickness as about 10% of the length. You know, if the wall thickness is more than 10% of the length, then you're not going to get very good results. And this approach assumes that the shear stress is the same all the way through the wall thickness. We saw that, so that's what being a thin wall lets you do. We saw with the circular cross section, since the shear stress due to torsion depends on that row vector, we know that there really is some dependence on how far you are from the centroid. But if the wall is thin enough, you can throw that out and just, it's a reasonable approximation to assume that it's the same the whole way through. So the examples of stuff that we can do, I already did a picture sort of like this, but hollow circular cross section. That I drew the rectangular one before. We can also even do shapes like this. As long as it's closed, as long as it's a sealed wall that encloses some area. One thing that after we talk about this we'll be able to do is this, a thin-walled circular cross-section, we'll be able to do two ways. And anyone who's taken classes with me before knows how much I love calculating the same thing two ways and comparing the answer. It's one of my basic joys. So we're going to do that.
That's only on the circular?
Only on the circular, yep. Because we can use the circular approach and we can use the thin-walled approach, and then we can see, one thing we can use that for is to get a sense of when the thin-walled approach starts to deviate from the correct answer. You know, you can think of the circular approach as giving you a more accurate answer, and you can compare them. It must be a closed cross-section, a closed shape, so no I-beams, no C channels. So that's too bad. Those are useful things in engineering applications, but those are more complicated calculations. Okay, so again, we're going to choose a temporary capital XYZ coordinate system. With the capital Z axis pointing as an outward normal to the wall. So like, for example, if this is the shape and this is your desired point, then the z-axis is going to point this way, the capital Z-axis, and then the y-axis has to be pointing that way. Then the shear stress, and again it's a capital X, capital Y shear stress, is equal to the negative torque divided by 2 times lowercase t times a sub m, where lowercase t is the wall thickness at the desired point, and A sub m is the area inside the wall median. I'll draw a picture of what that means. Okay, so if that's the cross section, the wall median is halfway between the inner and outer wall all the way around. So that's the wall median, and the area inside is all of this. That's not a really like a physically important value or anything. It just is a sort of a funny coincidence when you go through the derivation that some terms combine and you can end up representing it this way. But so the red shaded region is the median area. And then, again, you have to use rotation matrices to go from that capital X, Y, Z coordinate system to the real coordinate system.
So it's the 1/2 OD minus ID.
Which one?
Times the area, the median.
It is, so you just have to figure out, so like if this had an outer radius, it's easy with a circle.
Yeah.
If this had an outer radius of 0.1 and an inner radius of 0.08,
Right, okay.
then this would be 0.09. This would be a circle with a radius of 0.09. One thing that's probably worth keeping in mind is we're talking about thin-walled tubes, usually thin enough that the area inside the outer wall isn't too much different from the area inside the inner wall, isn't too much different from the area inside the median of the wall. So as a quick approximation, just take the area inside the whole thing, you know. Or as an even better approximation that's not totally accurate, but calculate the area inside the outer wall, the area inside the inner wall, and average the two, you know. So don't spend a ton of time worrying about that median calculation. Okay, I think there's one or two problems on the homework where really calculating that median area, it's possible, but it's kind of a pain. Don't even worry about it. Take the area inside the outer or the area inside the inner or both and average the two. That's right. That's right. So for safety purposes, yeah, you'd be better off with that one. You're right. Yep, that's a good point. Okay, well, let's do everyone's favorite thing to do. One single problem, two different ways. Compare the answers. Okay, so here is the example. So let's say that we have a hollow tube. If you don't like doing this, I urge you to reconsider. And we're applying a torque to it of 15,000 Newton meters. And we are going to calculate the stress. So if this is the coordinate system, we're going to calculate the stress at the outer wall and the inner wall and compare the two methods. So we're going to calculate the stress at A and B using first the thin-walled tubes approach, and second the circular cross-section approach. For thin-walled tubes, we're assuming that the shear stress is the same all the way through the wall, so we're just going to do one calculation, and that's going to represent the stress at A and B. For the circular cross-section, it depends on that rho value, so there is going to be a bit of a difference between those two, but we'll see that it's not very much. And let's, for the cross-section, let's say that the difference is the inner radius, let's say, is 0.35 meters. Wow, that's a big radius. And the outer radius is 0.4 meters. Okay, so first, does it meet that 10% thing? Well, the whole width of the side, length of the side is 0.8. So the thickness of the wall can be up to 0.08. And in this case, the thickness of the wall is 0.05, so it fits in there, although it's getting sort of close to the boundary.
You gave us a length somewhere, sir?
The diameter. So the diameter of that thing is 0.8 meters.
Okay, yeah. Oh, yeah, okay, I get it.
Okay, so first thin-walled tube. In both of these, we're not going to have to worry about the rotation matrix because tau, capital X, y is equal to tau lowercase x, y, so what we get is the final thing we need. Okay, so tau, capital X, y is equal to, oh, first we have to calculate that internal torque. Well, negative torque divided by 2 times the thickness times the area of the median of the cross-section. Yeah, I'll give you all these. So this torque, this internal torque, can you eyeball that and tell me what that's going to be? Should we go through that calculation? If you think of doing a cut here, you'd have a torque on the left that's equal to negative 15,000. That means the internal torque has to be positive 15,000. So this value has to be 15,000. But if you ever, get confused about that, just go through the internal loads calculation. It doesn't take much longer. What's the thickness of the wall?
0.05.
Yeah, 0.05. And then the median, the area of the median, our median is 0.375. So the area inside the median is pi times 0.375 squared. And you get 0.442 meters squared. So this shear stress is equal to negative 15,000 divided by 2 times 0.05 times 0.442, and you get a value of negative 3.39 times 10 to the 5th pascals. And that's also equal to the XY shear stress in our lowercase coordinate system, our real coordinate system. So that stress tensor is equal to 0, negative 3.39 times 10 to the 5th, 0, negative 3.39 times 10 to the 5th, zeros. And that's true for both the points A and B because of the thin-walled assumption. Any questions about that? Okay, anybody have a guess at what? So we're going to get two different answers. We know for the stress at the outer wall and the stress at the inner wall when we do it as a circular cross-section. What would you guess is those two answers are going to, how are they going to compare to this answer? It probably, your first guess is probably about what's going to actually happen. Well, where is the stress going to be bigger? Think about the equation for a circular cross-section. Is the stress bigger on the outer surface or on the inner surface? On the outer, because rho is bigger. And so you might, I mean, not really based on anything, but you might think like, well, okay, if this represents somewhere in between the inner and outer, then I guess that the stress magnitude is going to be bigger on the outer surface, smaller on the inner surface, and that's what it's going to be. Okay? So now the circular cross-section approach. Our capital X, capital Y stress is equal to negative fancy T times rho over I sub P. And again, our capital coordinate system is in the same orientation as our real coordinate system, so we won't have to use the rotation matrices. I sub P is equal to pi over 2 times the outer radius to the 4th minus the inner radius to the 4th. And that is 0.01664 meters to the 4th. So at the point, where did I draw this point? At the point A, that's on the outer surface. So at A, tau xy is equal to negative 15,000 times 0.4 divided by 0.01664, and you get a value of negative 3.61 times 10 to the 5th pascals. So the stress tensor at A is equal to 0, negative 3.61 times 10 to the 5, 0, negative 3.61 times 10 to the 5, and now we'll do the same thing for the inner surface. At B, that's the inner surface. Tau xy is equal to negative 15,000 times 0.35 divided by 0.01664, and you get a value of negative 3.16 times 10 to the 5th. So the stress tensor at B is 0, negative 3.16 times 10 to the 5th, 0, negative 3.16 times 10 to the 5th, so the answers using the circular cross-section bracket the answer that we got using the thin-walled approximation. Notice that these answers aren't really that great. You know, there's a pretty fair percentage difference between the answer we got with the thin-walled approximation and the answers that we got using the circular. And that's because this wall really isn't that thin, you know. But we're not going to do this calculation, but let me tell you what would happen. So a couple things to notice. First, the inner and outer surface answers for the circular cross-section bracket the thin-walled approximation. Second, those answers roughly agree. But there's, I don't know, a bit of disagreement. Because the wall thickness is pretty big compared to the diameter of the tube. Okay, so what if you did this problem again? and you said so let's do a new example. We're not going to actually do it. I'm just going to tell you what the answers are. So again, we have a circular, hollow circular tube. This time, for some reason, I put a 10,000 Newton torque on it instead of 15,000. And think about these points A and B again. And this time the cross section has an outer radius of 0.4, like it was before, but an inner radius of 0.39. Well, the thin-walled answer says the XY shear stress is equal to negative 1.02 times 10 to the 6 pascals. By the way, why did that stress get bigger even though I reduced the torque?
Smaller row?
The row isn't any smaller, but it's less cross-sectional area trying to withstand that torque. And using the circular approach, tau xy for the outer surface is negative 1.03 times 10 to the 6. And tau xy for that inner surface is negative 1.01 times 10 to the 6. So you can see that as as the wall thickness goes down, you start to get much closer agreement between the thin-walled approximation and that circular approach that we can think of as our better calculation. Well, it's our better calculation for circular cross-sections. Anything that's not circular, we don't have that option. We have to use the thin-walled approach or else we can't do anything. Any questions about that?
I have a question.
Yeah.
How would we approach this problem that has a tube, but inner circle is shifted off the center of the outer circle, so basically you have one side is thicker than the other?
Yeah, that's fine. We can do that with the thin-walled approach. If you add, I mean, it's still, the wall still has to be thin, but if you add something like this, and say you wanted to calculate the stress at this point here, then, so that's your desired point. Then the thickness that you use is just this. And the median area is, you still calculate that the same. So yeah, we can, it's no problem to have the wall thickness varying. You just, whatever point you're looking at, you use the thickness for the wall at that point. Any other questions? Okay, that's all.